Hello everyone and welcome, and this is now the real stream. Unlike earlier where we had tests. Yep, we were testing earlier. Now this is the actual stream, and welcome to Freaky Physics. For today we have another lesson in physics with Gita. So I think she's already on board. Let's see. Okay, she's not here yet, so let's just wait. So anyway, from the looks of things, this is electromagnetic induction we're doing today. So, all right.
Hello.
Hello, Gita. And just say
Hi.
hello. All right.
We'll see.
How are you feeling now?
Better. I don't feel sick anymore.
All
Not
right.
that much.
All right. That's good to hear. Okay. So, all right. Well, I just gotta point something out from last week about the two graphs that we were doing, and I said I couldn't think of the proper answer anymore because I was that tired. Uh,
Yes.
I was looking at it and then I realized something, and I just confirmed it further um with a with a search online, and basically what I got was uh if you have an if you have the isochoric process, or rather, if you go back to A. So let me just show you the screen first before we do anything else. Where is it? Here we go. Okay, so it's still here. I just want to show you what it does. So basically, because here we start from A, B, C, and then we go back to A, right?
Yeah.
So the one thing that we can add here is that if the process is cyclic, so this means that the internal energy delta U equals 0 for a whole cycle. Okay, so that means I just want to go back to this. We're not gonna go through 8 anymore. I'll just go through here in the first part, here in 7. Yeah, so that means this is not just any value x. This has to total to 0. So we have 970 here, right? So in other words, when you add all of these, these should be 0. So in other words, this should be um, 1570 minus 700 and 970. Okay, so that's
Oh,
how. Go ahead, ask that again.
why do they have to add up to 0?
Um, because it goes back. So think about it. If it goes back to its initial state. So the internal energy has to go back to the original state as well. Get you on?
Right.
Okay,
Okay.
you get it. You get it. So in other words, let's just do
Yeah.
1570 minus 970. That's why the answer here is 600, and um therefore this must also be how much? This must also be um well, we add these up. This should be 1,000, so this should be 400. Okay, so that's why this was 600
Yes.
to start with. All right. So the other one's similar. Number eight's gonna be similar, but like I said, we won't go through the full solution. But you can turn it cyclic by making it go this way. And when you make it go cyclic, you can solve for the reverse of A to C instead of from going from C to A. And then from there we can solve stuff. Okay?
Even if the cycle goes C to A,
Yeah.
kind of.
It has to go from C to A because otherwise it won't be a cycle, right? Going A to C won't
Yeah.
go back. So, all right. So we'll skip that for now, and let's go to the question sent over, which is basically about magnetism, electromagnetism, right?
Yes.
Mm. Uh, all right. Which one will we do first? Let's do the multiple choice questions first, yeah?
Okay.
Okay. So here, the first three questions, you have a uniform for the first one that I'm trying to paste. We have a uniform magnetic field. Oh, by the way, I'm on stream. I am not presenting my board yet. There we go. Okay. So, all right. So here, okay. So here you have a uniform magnetic field. This magnetic field strength is given as B. It completely links a coil of area S. The field makes an angle theta to the plane. The magnetic flux linking the coil is what? This is actually the way magnetic flux would be, the area is S. So by the answer here would be not A, definitely, and not D. It's either B or C.
Why?
Okay, the reason is, I won't tell you the answer yet. The reason is because the idea here is, let's keep it as a simple one first. Let's not go into this general case. The simplest possible case we can think of is if you have this area, let's just say this, it doesn't really matter what the area is. So let's just call this S for now, right? Okay. And then the simplest possible case is that your magnetic field is perpendicular to that surface. Okay. In this case, the magnetic flux linkage here, the magnetic flux here would be equal to, this is magnetic field strength B. Yeah, that's just gonna be BS. You know what? I'm gonna change that to A just to make it more consistent. I think S is specifically for this case. Yeah. So let's do it A here and A here. Yeah. Now, here's the thing though. There is an angle of 90 degrees here. So I want to add that 90 degrees in there. Okay. But we know it's not going to be 0. So this has to be either sine or cosine. And for this to be 1, this has to be cosine. Sine. Yeah. So that's the way I incorporate that 90 degrees in there. So this is one way for me to remember which one is which. So from here, I can already say that the answer is what? The answer is not B. The answer is C.
Sorry, but I don't really understand where the angle is coming from in this situation.
Okay. The idea here is this. Because okay, it's not so clear what the definition is just from this example, right? So let's clearly define that. The definition, let's do it here. So phi, this would be the magnetic flux. Okay. Now let's also keep this. This is magnetic flux density. Now we normally call this magnetic field strength, right? But we'll use this other term, magnetic flux density. Or this is, I'll just put it here, same as a magnetic field strength. Okay. Okay. Now, and then of course the last one here is we will define A as the area of some area through which the magnetic field passes through. Okay. Okay. Now the idea here is this has to be passing through, because there is a relationship between these three things. There is an equation relating these three things. The just from here, B, the magnetic flux density, should be equal to the magnetic flux divided by the area. Now, what does that mean? The way I think about it, and this is going to make it a bit more visual in terms of what's happening, is if we compare two areas like this one, let's make it easy. This has 5 magnetic field lines passing through it. This one will only have 2 magnetic field lines passing through it. So the first one, this is gonna be the stronger field, right? Stronger field. So this is how you think about it. Because it's a stronger field, there are more magnetic magnetic field lines passing through that area. Okay, and if you have more magnetic flux, magnetic field lines passing through that area, you have a bigger magnetic flux density, because the magnetic flux, you can think of this as the number, and it's not really a number, but it in the visualization it makes it easier. Okay, this is the number of magnetic field lines. So I'll say total as well. Okay, all right, does that kind of make sense?
And in an experiment like a coil,
Mm-hmm.
and like that is being induced
Right.
with a current, what is like, because we did it in class and we put some angle up, but is that the angle of that the magnetic field is
Yeah.
against?
Right.
That?
Yeah, that's right. Because the idea here is the bigger the angle. Think about it this way. Okay, so this is the case here without the angle, right? So now that we're gonna do the same thing, and then let's say we have, so let's introduce angles, right? Introduce angles. Now, let's say we have this particular area here, and let's just draw that now, wherein the angle here is gonna be 90 degrees, right? And then there's a second one here wherein it's coming at some angle, let's just say theta, like this, and let's keep it consistent with 4 field lines passing through like that. The angle between the area and the magnetic field is theta. Okay, now if you think about this, because of that angle, there's let's consider just one. There's gonna be a component, let's say that that's the how do we say this? Okay, let's say that this has a magnetic field strength B for now. Okay, and both of these would have a magnetic field strength B. Okay, so what's gonna happen here? Here, all lines pass through the area, right? Pass through area. Okay, now here on this second part, only the component bx, by rather. So this is gonna be by this way, and there's a component bx going this way, right? So because magnetic field lines are, hold on, I keep getting messages. I will close it first. Okay, just so it's easier. Okay, so all right, so only the component by passes through the area, right? Passes through. Bx does not, right? That's the reason why we need to consider the angle. So in this case, by, we can already see here. So if I'm gonna do that further, so this is gonna be b, this is gonna be by, right? And where is our angle? This is our angle theta. So from here, we can see from the triangle we formed that by over b is equal to sine theta. Okay, so in other words,
Yeah.
by should be b sine theta, and therefore that's the thing that goes in this is the only component that passes through the area, and therefore we need to incorporate the area in the formula for here. Okay, so what does this mean? So I'll just summarize this first. So what do we get here? So that means that the flux linkage is actually gonna be by times the area, and that's gonna be b a sine theta. Okay, all right, any questions?
What is blocking the thing from passing?
There is nothing blocking it, but the way that this works is this is actually because of vector, something called vector multiplication. And there are two ways to multiply vectors. But either way, for vector multiplication, you either consider only the parallel components or the perpendicular components. In this case, we consider only the parallel components.
Oh,
Okay?
okay.
So the perpendicular component has no effect, so we ignore it. So we only go to this formula. That's why we have the sine theta in this case.
Okay.
Right? Okay. So since that's the flux linkage, that's the magnetic flux, that's gonna be BA sine theta, and from here, we just replace the area with S, so that's gonna be BS sine. Our angle now here is not theta but phi, so BS sine phi. So here, so that's why our answer here is C. Okay.
So we just followed the formula.
Yes, in this case.
We just picked the okay.
Okay. Let's go to the second question. So a magnetic field links a closed loop of metal wire. Okay. The magnetic field strength B varies with time t as shown. Okay. A current is induced in the loop only which time? Okay, let's go back here. I'm pretty sure you learned the algebra version of the formula and not the calculus version, so I'll just write the algebra version. The EMF, let's go back to the formula. This is in the formula booklet, by the way, right? The EMF would be this N, then delta phi over delta T. Okay. I just want to note what this N here means before we go to the question. Okay, N here is the number of loops in the wire. Okay, so for example, where's my here? Okay, so for example, let's just go back real quick. Okay, this is one loop of wire. This is one loop of wire. That's two loops of wire and three loops of wire, etc. Okay. So the thing here though is, if you look at this, if we look at this particular segment of the equation, oh, I forgot one thing here. There should be a negative here. Okay. But the negative doesn't really matter for the exact value. The idea here is if we go back to this and focus on this part, okay, so if you look at this in terms of the graph given, this is basically the gradient or the slope, right, of a phi t graph. Okay, so what does this mean? If that's 0, then you don't have EMF. Okay, otherwise you have EMF induced. Okay, so let's take a look now here in the graph. What's happening here in the section T1? B is changing, right? Same thing with
Yes.
T3. B is also changing, but here in T2, that's approximately a horizontal straight line. So in this case, we can say here that the gradient is 0. And therefore, because the gradient is 0, you don't have EMF formed there. So the only time we have EMF induced is T1 and T3. So the answer here is D. Okay?
D.
Yes.
But if we model this, it would be the I feel like so close. The whatever's induced going slowly towards, but afterwards for T3, isn't it going down?
Yes, it is going down. But specifically, this section of T3 could be considered a no EMF zone. But the rest of it, because it's still changing, there is EMF in being induced there. Okay.
Okay, so it can be negative.
Yeah, it can be negative. By the way, I'll just rewrite this in a different form. E equals negative n. Change in, then I'm just gonna say BA over delta t. So this can also be interpreted as the gradient of, oops, gradient of BT graph. Okay.
Okay.
All right. Let's go to the third one. North pole of a permanent magnet is pushed. You know what? This is really. I think you're still confused over what's actually happening with this question,
A
right?
little.
Okay. The pointer to the sensitive pole moves to the right and gives a maximum reading of 8 units when it's pushed in. Okay. The experiment is repeated, but on this occasion, it's the south pole at twice the speed. So, okay. Twice, south pole at twice the speed. So that's gonna double. That's really gonna double it. So our answer is either C or D. Yeah. But since you reverse the magnet, you're gonna reverse the direction of the current. So I'll just do the shortcut here, yeah, before we discuss further. So shortcut first. Shortcut. Okay. The EMF is proportional to the velocity of magnet. Okay. Properly, I'm just gonna say it. That's a shortcut, but properly, this is actually the EMF is proportional to the rate of change in B. Okay. Now, in this case, because you double the velocity, you're doubling the change in B. So that's gonna work in this case, right? The other shortcut here is there are four things to flip, four things to change in these kinds of problems, in solenoid, magnet, induction problems. Okay. By the way, this is magnetic induction. There are four things to change. One is orientation of the magnet, whether it's north pole closer or south pole closer, N or S closer. Yeah, closer. The other one is direction of motion of the magnet. Direction of motion. Okay. The third one is position of the magnet, left or right of the coil. Yeah. Position of magnet, left or right. And then the fourth thing that you need to consider that you can change is the direction of solenoids turns. Okay, turns of solenoid. Okay, most of the problems, in most cases though, this is the last one you should consider because that's not normally seen in problems. Okay, so normally you see the first three. Now, the thing about this is the reason why I mentioned these four is because when you put these four together, okay, so each for each one, reversing it reverses the current. So if you reverse two things, you're basically doing a double reverse, so you don't do anything. Okay, so again, this is the shortcut first I want to discuss. So let's take a look here. What happened here? Initially it was north south like this and going in like that, right? Okay.
Yes.
Now the new one is you reverse the magnet. South is here, north is here. You're still going in that way, but direction of motion is 2 times the speed, right? So how many reversals did you do here? Again, the doubling is not a reversal, it's just a doubling. So that makes it That makes A and B incorrect. Okay, it has to be 16. But how many reversals did we do? It's only one. We only reversed the magnet.
Yes.
So our answer here, is it C or D? Earlier, it moved it to the right. So now,
So now it's to the left.
it's now to the left. So this is the correct answer.
Okay. And how can we know which part of the coil is north and which one is south?
All right. So this is actually, you know what? I just discussed this with another student literally a few hours ago. Okay. All right. I'll give you the short version just to make it easier. Yeah. It's always like this. You see, I'll just say the name of the law first. Lenz's law. Okay. Lenz's law will basically, basically any change is opposed by the EMF induced, yeah? By the induced EMF. Now, that's how it's that this is normally how it's said in textbooks, but there is a shorter way to think about it, okay? Just think about it this way. I'm gonna draw all the possibilities first, just so you see what's happening. Okay, so I'm not gonna draw anything else, not the galvanometer yet, okay? Or rather, I'm not even gonna reverse. I'm just gonna say coil. I'm just gonna say coil like this, okay? Hold on, let me redo that. Okay, so this is our coil. Okay, and there's our galvanometer. I'm just gonna write G for there. And then this is our magnet, right? Now, let's put a north pole in here. Now, the idea here is, the way I would ask you to do it now is to do this. The coil, I'll just write it like this. The coil opposes magnet movement. Let's just do it like that first, okay? It will always oppose the magnet movement. I'm not saying that it will oppose the poles. It's gonna oppose the movement, okay? So in this case, if there is no movement, because there's nothing to oppose, this is no pole here. That's it.
There's no
if there's no movement, there's no pole.
Even if the north is next to the north.
Yes. Okay, because it will always have to oppose the movement, and it's not about the magnet itself. It's about the magnet moving. Okay, now that movement is relative, so you can move the coil to the magnet or you can move the magnet to the coil. Either way, the effect is the same. All right, so let's go. So let's do the second case. This is again the coil, and let's just put the galvanometer here, right? So in this case, the galvanometer doesn't register a reading, right? So here, let's make this magnet a north pole on this end, but this time it's gonna move that way. So again, go back to the idea that the coil will oppose the movement. If the north pole is going to the coil, how will it oppose the movement? So I'll write it here. N coming close. Coming close. So coil opposes by,
it's gonna push it the other way.
Pushing it the other way, right? Push the other way. Pushing other way. And how will it do that? With a north or a south pole?
North.
And that's the key part here, with the north pole. So in other words, this gets an N. This gets an S. Okay? So, I'm gonna make here that this is an assumption for now. Okay? So I'm gonna make in this case that the assumption that the current makes the galvanometer move to the right. Okay? Now, let's do a third one. Same thing, same idea. So this is your coil again. This is your galvanometer. Okay, there's your galvanometer. This is your magnet. This is a south pole. It's going away.
It's gonna
Again, oppose
oppose
the
it with
motion.
south.
Now think about it. If this were south, it's gonna help it because it's gonna repel it further, right? It doesn't oppose the movement of going away.
Oh, yeah. So north.
This has to be north. Okay, so let's write that again. So okay, so away, right? So coil opposes this, right? Opposes by, I'm gonna use the word attracting, right? Attraction. So because it's gonna oppose it by attraction, that has to be north. Okay.
Okay, and can I ask another question?
Go ahead. Go ahead.
It's like, when we have it connected to a circuit,
Mm-hmm.
and it induces a magnetic flux,
All right.
why does the current not stay in the circuit?
It does, but how to say that? It does that, but okay,
Because we have an ammeter and it says 0.
oh, okay. Question is, it does, but because here's the thing. Ideally, it should keep going. Ideally. But in reality, it doesn't because there's resistance in the circuit. The resistance takes away energy, right? It slows down and eventually stops.
Right.
Okay. So again, so is it actually possible to have that kind of circuit? Actually, it is, as long as you have zero resistance in the circuit. And we have made materials to do just that. The problem with those materials, just so the story though, the problem with those materials, they work at sub-zero temperatures. Liquid nitrogen temperatures. Yeah. All right. So anyway, let's do one more here before we move on. This time around, here's your coil. You still have your galvanometer here. And this time, I have a north pole going... No, not a north... yeah, a north pole going away. So what's gonna happen here?
Sorry, I didn't hear it glitched.
Sorry. All right, so we have a north pole here going away from the coil. So what pole is induced here?
It would make a south pole and pull it in.
South pole, correct. So this is gonna be a north pole. So okay, with our assumption that north on the right makes the current go this way, which way will the current go here now? Because you reverse the poles on the coil, that would also reverse the current. Okay. So in this case, the galvanometer will point that way. Okay. All right. Okay, so that question is done. That set of questions is done. Excuse me. Okay.
Wait, sorry.
Go ahead.
The galvanometer points opposite the direction of the...
Yeah, because the polarity of the magnetic poles got switched around. So that means the current will also move the other way. Okay.
If it goes north to south, it would go through downwards.
It's not always going to be the case. The idea here is because, how to say it? It depends on how the wire goes around the object. Where is my tube here. Okay, so I have here a tube just to show you what I mean. Okay, let's go to the main camera first. Where's my cable from earlier? All right. Here. All right. Okay. So here's the idea. Okay. Let's say I'm just gonna simplify this. Let's say that I'm wrapping the cable around this way, so you can see that it's like on the closer side to you, the plug's coming out like this, right? So the effect is gonna be different if you wrap it around the opposite way, like this. Okay, so something like this. The effect would be different, and therefore the direction of the current would be the same. Would be different as well. But in this case, we are gonna assume that it's wrapped in a certain way, so that the galvanometer needle points in a certain way. So just because this is north doesn't mean that the current will always flow this way. If I reverse this, again, if I reverse this, and this is still north, because this got reversed, the current's gonna flow the other way. So it's gonna flow down this side, not and flow up this side. Okay?
Okay.
Alright. Okay, so put that to the side. Okay, let's go to the next question here. Okay. Magnet is suspended above a coil of wire. So let's do this bar magnet above a coil of wire with a spring. Okay. Explain in terms of change in flux linkage while the reading on the voltmeter is alternating. Okay. This, were you able to answer this question? Okay, hold on. It's still, image is still loading.
No, because I didn't understand.
Okay.
Why? Because it was before I didn't know about the current, and the actual linkage was
okay.
very
So,
short.
it's actually the way I see this problem. This is actually a little bit difficult, in all honesty, how to solve this. Okay, but okay, the image is taking a while to load. Let's refresh my board. Do we have the graph? Did you send over the graph? Not really. Yeah. Okay, so we don't need the graph there. So we'll just answer B, right?
Yes.
Okay, let's take a look at the idea here first. Let me share the other screen first. Yeah, let's share this step.
And the graph, sorry, the graph looks like a sine curve.
Yeah, it should look like a sine curve, right? Now, the idea here is, let's take a look here at this magnet. We know that for magnets, that the flux density, or let's avoid that term first. The magnetic field strength is gonna be strongest near the poles, and so with that in mind, so what's happening? You know what? I'm going to just draw this. It's taking so long to load. Let's go back here. Okay. This. I'm just gonna say weak and strong. I'm not gonna draw the whole field lines anymore, just to make it easier to see. Yeah. But the idea here is that when it's in its initial position at the top, so that magnet's gonna oscillate up and down and up and down and up and down, right? What's wrong with my board? It's just loading. All right, since that's not quite working, I will just go back to main camera first. Okay, so sorry, I'll just visualize with something. Okay, so we know that it's gonna be strong here and weak here, right? Okay, so what's gonna happen? Okay, hold on, let me stop sharing the board as well. Okay, so you can see me more clearly. All right, so let's say that this thing is a magnet, and this is the pole coming into and out of the coil. So this is gonna be the stand-in for the coil. Okay, So when it's here currently at the top position, it's weak. The magnetic field in here is weak, right? But as it goes in, what happens to the magnetic field inside this coil? It gets stronger and stronger and stronger, right? Okay. Once it's here and at its maximum position, it's gonna stop temporarily. That means at this point there is no motion, so there is no EMF. There's no EMF induced at this position. Then it's gonna go back up.
Okay.
Right? Now as it goes back up, it goes from strong to weak. There's a change. It's gonna be the exact same change as before because it's now from strong to weak, the EMF induced is reversed. Basically, it's like thinking here you're pushing in, here you're pulling out. So it's the same thing as before. So when it's getting pushed in, the current flows in one way. It's getting pulled out, the current flows the other. Boom, boom. So what's happening here at the top? It stops temporarily again. So the EMF here is 0, and then the cycle repeats. So that's why it oscillates like that. Okay, and that's why also the that's why the graph looks like a sine curve. It's exactly the same reason. Okay. Okay, and that's why the voltmeter reading is also changing. That's done. Okay. Alright, the board isn't loading. I think my internet's acting up a bit. Alright, let's go to 36 then. I'll just share my screen here again.
Wait, sorry. Can I ask a question?
Go ahead.
So, okay, we just explained for EMF, but I thought that is what magnetic flux is, the change. So what is the relationship between EMF and the flux?
Okay, so the discovery was this. The story is, and we use that every day now for generating electricity, right? But the story is basically when this effect was discovered, it was that what happened was the effect was literally what we were doing: magnet into a coil, and then seeing what the effect would be. Okay, and the effect is definitely a current. And here's the idea: you cannot have a current without an EMF. You need that EMF to drive the current through, right? And because of that, so it's gonna be easier to think of it in terms of EMF rather than in current, so that we can actually calculate how much EMF is produced. Okay. So that's why we have that equation from earlier.
And magnetic flux.
Yeah, the magnetic flux equation. Okay. All right. So okay. So let's just do that. I just want to share this. I'll just share. Oh, now it works. There we go. Let's skip that now. Let's go to the next question. Okay. Next question is this. Okay, so we have a bar mag. This time you have a small circular coil of cross-sectional areas given with 250 turns of wire. Okay, plane of the coil are parallel to and distance x from pole piece of the magnet. Okay, PQ is aligned normal to the pole piece. Okay, the variation of line. Okay, the coil is moved along PQ. All right, it's still not loading on here. Let me share this. Oh, never mind. It's working now. Okay. Alright, so let me share the screen again. There we go. It's finally working. Okay, here we go. So here. So we have this magnet here. The question is the more so that the distance x. Okay, so use Faraday's law. I think this is a continuation, right? So use Faraday's law to calculate the mean EMF induced in the coil. So we need this graph, right? Okay. So in this graph, let's take a look first at the change in the magnetic flux. Yeah. So what's delta B here first? The delta B is from where is it? From 6 to 12, right? So where is 6? 5, 6 will be here. 7, 7. No, 5, 6, 7, 9. So it's 1, 2, 3, 4, 5 times 4, 20. So the difference of 5 is 20. 6.25. Okay, every 4. So 1. So 6 would be here, right? And then the other one, 12. So 11, 11, 12 would be here. Okay.
Yeah.
Okay. So let's take a look at delta B. It's there. This is gonna be 3.3. That's 3.3, and then this is 1.67. This is 1.7. So delta B is equal to 3.3 minus 1.7. That's 2.3, 1.6. Okay, then let's take a look at the unit. This is times 10 to the minus 2 teslas, right? Minus 2. Okay, that's delta B. Delta T is given 0.35 seconds. Okay, what's the area? The area I think is given here earlier. Cross-sectional area is 1.7 times 10 to the minus 4. 1.7 times 10 to the minus 4 meters, square meters. And then finally, we need the number of turns. It's said here that the coil contains 250 turns. Okay, so N equals 250. So again, the induced EMF will be equal to N A let's just do it like that. NA delta B over delta T. Again, there's a negative sign in there, but we can ignore that for our calculations. So we just put our values in. Let's put that in the calculator. Not yet. Okay. So that's going to be 250 times 1.7 exponent negative 4 times delta B is 1.6 exponent of negative 2. Then we're gonna divide that by the area of by the time delta T, 0.35. Okay, divided by 0.35, and that's our final answer. 0.0019 volts. That is a very small number, but we do have very small numbers to deal with, so that's fine. Okay.
And if we found the gradient of the graph, what would we get?
In this case, we cannot do the gradient with this graph because our x-axis is not time, it's distance. So that's the tricky bit here. You have to look into your graph whether it's a BT graph or something else. In this case, it is something else, so we can't find the gradient. Well, we can, but it's not gonna be useful. Okay.
Yeah.
All right. So that question is done. Okay, you still have a few questions here about photocurrents and stopping potential. This is the photoelectric effect, if I'm not mistaken, right?
Yes.
Okay. Now, okay, do you have any questions about the magnetic field, about the magnetic fluxes? Questions? Is this more or less clear?
It's clear.
All right. Just so we know, I am expecting you to say no because this is a rather difficult topic. Yeah.
No, I really don't like this topic, but for now I understand the basics of the equation, so I think it's okay.
All right then. So let's take a look at the photoelectric effect. Why do we have these graphs? You all have similar graphs, so I'll just pick one. Yeah. Which
Okay,
one?
but my question,
Mhm.
my question was, what is the difference between them?
Oh, okay. Um, okay. I
It's
think
because
I think I'll get the two that are really similar, the ones that's given rather than the one that you have to graph, right? So let's copy this
okay.
and compare it to the other one. Okay. Um. Okay. Now, what do you know about the photoelectric?
I know that energy can be changed and the frequency can be changed of light,
Mm-hmm.
and it could make the electrons be emitted and
Mm-hmm.
put into a circuit.
Mm-hmm.
And the stopping potential um, is the frequency that is
Mm-hmm.
needed so the electrons don't pass through.
Okay.
And for these graphs, it was because I wrote some notes, and then in class, we actually said that if intensity increases, the frequency doesn't, or something.
Mm-hmm.
And I don't really understand, because how can intensity increase and the frequency not?
Okay. Now, okay, I'm just gonna get some. Okay, let's see which one is similar to what you have probably studied. Where is that equation? Okay, so it's loading again, so I think I'll just present the actual images first. So let's share this image. So that's the first one we wanna go through. Okay, so in this case, there is the main difference is that for a graph using the photoelectric effect. Okay, hold on. Okay, now it's working. I'll just go back to this now. Okay. Where's
Mhm.
the other one? Do this. See if this pastes over. All right. So anyway, for this one that I'm sharing with you, okay. What's the difference here between the photocurrents? First of all, which one has more energy? Which one has more energy? Blue light or red?
Blue light.
Blue light. Okay. So since blue light has the higher energy because of its higher frequency, then that means you don't need as many photons to start the photoelectric effect, right? So what's happening here? What does this graph mean? Photocurrents. Okay, so this is the applied potential difference. I think you're getting confused because you don't know what the graph actually means.
Yeah.
All right. So okay. This is what we'll do. I'm not gonna share my board here at the moment. I am going to share a simulation. This is so much easier with that simulation. Let's see if it's here. Let's see if it's still available online or just a different version of it. Photoelectric effect. Ah, okay. We have a PhET simulation. We can, but it's the Lego. It's the Java version. Okay. Okay. Let's think about it this way instead. Okay. While I'm just gonna show the image for now because I have to run the simulation. It's gonna take a while to download. Okay, so here, what's the idea here? You're shining light onto the metal, and then it's gonna go through here, and it's gonna go through the circuit and everything, right? Now, think
Yes.
about it this way: because these electrons are moving, that means they have some energy. This also means that if you have the correct voltage on the battery, you can stop these electrons because basically you're providing energy to the electrons to travel the other way. Okay, so let's zoom in to make it easier to see. So you get the idea. The electrons, due to the photoelectric effect, are going from left to right, but because of this battery, they're gonna go right to left. So you're trying to find the point at which this voltage balances the photoelectric effect. Okay, so that's
What would the voltage? Sorry.
Go ahead. Just ask the question.
What would the voltage do to make the electrons move around?
Just think about it this way. If you don't have the light, and then this was a complete circuit, the electrons would move, in this case, would move counterclockwise, right?
Mm-hmm.
Okay, so hold on, let me check. Okay, there we go. Okay, in this particular case, let's see if we can show that here. All right, so again, if the light wasn't here and this was a complete circuit, the electrons would move around counterclockwise, right? Now, the idea here is, that's because the battery gives energy to the electrons. Now, if we ignore the battery for a while, then the photoelectric effect gives energy to the electrons, but they're gonna go the other way, right? So I'm gonna set it up so the battery is gonna oppose it. I could set it up so that the battery is going the other way, but that's gonna be a bit more difficult to find something useful. Okay, so to make it more useful, we will oppose the photoelectric effect with the battery. Okay.
Yeah.
Okay. Now what's gonna happen here is once it's opposed, I could change the frequency of the light, right? But if I change the
Yes.
frequency of the light, because of the fact that the energy of the photoelectrons depends on the frequency of the light, I'm gonna have to reduce this voltage to just balance it. If I keep it at 8 volts, it could be too much. Yeah, and then I just get the reverse of the photoelectric effect, right? So that's what this is. Now, if we go back to the applied PD in the graph, that's exactly what it is. That applied PD on the graph is this battery in this setup. Okay, so let's share this now again, and there. Okay.
And
Okay.
why did the lines cross over in graph B?
Okay. Now, okay, first of all, in graph A, it's easy to see because they're the same frequency. They're identical photons and therefore they're the same frequency, right? Now, they cross
Yeah.
over here because the idea is one of them um, needs a bigger applied PD. Going back to our image earlier, again, you need a bigger voltage for the higher frequency light, right? So the idea here is this is the higher voltage. Higher voltage.
To stop them.
To stop, right? To stop electrons. So this means this dotted line must be must have the higher frequency and therefore blue light. Okay. Now, them crossing over is just gonna be a feature of the photons themselves. They don't, the crossing over point, there is no significance to it. Okay.
Okay.
The only significance here would be at this point, just that it's just a mathematical significance that at this voltage you have the same photocurrent, but otherwise no physical importance. Okay. It's more a math thing. The other thing here is the last one. If we go into the equation of the photoelectric effect, let me look for the equation again. Where's a good version of it?
I can find in the format of it maybe.
No, I'm just looking on the internet that I can copy and paste straight away. There is one. All right, I'll just copy this one. It's not so good, but at least it's explained. Yeah.
Okay.
Okay, we're using different symbols from what you probably studied, but idea is still the same. Okay. So in this case, the kinetic energy of the photon is equal to the photon energy of the electron, right? So this is about the electron. So this is the electron. This is the photon. And this is the metal, right?
Yes.
Okay. So the idea here is how does this equation relate into the graph? There was a question you sent earlier about the last one, stopping potential. Okay. Actually, no, that's fine. I think we don't need this now. Okay. So Okay, never mind then. I think we're done there. We'll just keep it there. Okay, so with these graphs, let's just stop here at these graphs. So this means that these higher voltages to stop the electron, that's why it's called the stopping potential, because you have to stop the electron. And then voltage, the more accurate term for that is potential. Okay, not just voltage. Okay.
And does that mean that electrons with just a certain voltage can pass through? The one that's
In this case, no, because this would be okay, I think I'll just say it here. I'll add I'll add a term here. Okay, so in this case, the stopping potential. Oops, I'll do that. Okay, okay. So in this case, the stopping let's label that here. So the stopping potential would let's label this stopping potential. Okay. Now, it's the voltage. I'll just put it higher for the blue light, but the stopping potential is the voltage to stop the most energetic electrons. Okay, because of the fact that we have the electrons that come out of the photoelectric effect, they don't have the same amounts of energy. Some have more energy than the others. In other words, they're moving faster, right?
yes.
Okay, so the stopping potential is enough to stop those fastest moving electrons, which means it should be able to stop the lower energy electrons as well. Okay. All right, so that's basically it. So, okay, I think that's it in this case. All right, so next meeting, just let me know if you're able to book the rest of the meetings, because I think the subscription's finished for this month, right?
Yeah.
Okay.
Yes, I have to rebook it.
All right. Okay. So just book it whenever you can, and I'll see you on the next lesson. Okay.
Okay. Thank you so much.
You have a good day, and I'll see you again next time.
Have a nice day. Bye
All
bye.
right. Bye bye now. Okay. So that's the end of the stream. So hopefully, if anyone was listening, I don't think anyone was listening. Oh, somebody's viewing. Hi. All right. So, anyway, so that's the end of that lesson. It is a bit long for today, so we'll end it here. But before we do, don't forget to like, share, and subscribe to the channel. We're on YouTube, Facebook, TikTok, and Instagram, and when we stream, we're also on Twitch. Again, so with that, we'll end it here. So I'd like to bid you all a good morning, good day, good afternoon, good evening, good night, wherever you are in the world, and stay freaky, everybody. Bye bye now.